Let me start thanking the organizer for the opportunity of being here. It's a real pleasure to be in this place after so many years. I still have very fond memories of the time that I spent here, and introducing the David class lecture, in which you're going to have Lars Peter Hansen as our keynote speaker. Lars is a David Rockefeller Distinguished Service Professor at the University of Chicago, and also the recipient of the 2013 Nobel Prize in Economics. And as most of us know and understand, Lars' work has changed quite significantly the standards of our field, raising the intellectual honesty in which we treat the limits of our profession, and integrating in our analysis, what we know and what we don't know. And in terms of the GMM approach, it was a big contribution for the empirical economics in taking into account that we should and we can test the aspects of the theory that really matters for the theory, and at the same time pretending that you don't control the full empirical environment. And then on the work stream, the whole work stream on robustness, he turned uncertainty into a formal object of analysis, in which we could exploit how agents and policymakers should decide when they do not fully trust their own models. So it's a great pleasure to be here, introduce Professor Hansen. After his whole career of not only developing those approaches, but also applying in very central issues of our profession, in asset pricing, microfinance, climate change risks, and more recently, and I have been the privilege of enjoying this partnership with him on carbon price and forest dynamics. So please join me to welcome Professor Hansen on this lecture. Thank you.
Yeah, thank you very much. Hopefully my voice is going to hold out here. I'm a little bit hoarse, but anyway, we'll give it a best shot. So I'm going to kind of revisit something that's very common in both public finance and environmental economics, and I'm going to try to pose it in ways that I think are more useful for measurement. I'm going to pose it in ways that I think are more useful for understanding how models behave as well. So this term, this marginal valuation in intertemporal context, of course, has been used extensively. So I'm certainly not embedding that term or its use. But I'm going to try to frame it in a little bit different ways, in ways that I think can be very valuable, and I'll try to clarify what those are. I have multiple co-authors on this and different aspects of kind of what of this research. So this kind of began by me trying to, I was trying to digest this literature on the social cost of carbon, and that literature has recently become a race to infinity, so it's become less interesting over time. But exactly what's the conceptual coherence behind it, and kind of how can we make sense out of what the measurements are trying to do? But this extends to a variety of other things in terms of nature-based capital and a variety of other objects. And part of the issue here is to provide a framework to expose where the modeling challenges are as well as the measurement challenges are. But anyway, these marginal valuations are certainly used in a variety of settings in public economics, environmental economics, macroeconomic policy evaluation. And they are used in two different ways. And the social cost of carbon literature gets these, lumps them together, but these are done in different ways. One is to navigate movements from some suboptimal allocation to a more efficient one. And the other one is to kind of provide interpretations of first order conditions for optimal policies and for designing things like Peruvian taxes to fully address externalities. So they can be used to kind of support implementation of optimal policy or say some robust counterpart. So roughly speaking, they're going to be kind of proportional to derivatives of values and stuff like this, and with endogenous state variables. So I'm going to start off by providing a little bit different formulation or formulas for these intertemporal marginal valuations. And they're going to open the door to kind of measurement challenges, but also for taking models with multiple dimensions to them and seeing how you can deconstruct them to figure out where the uncertainty matters and where it doesn't, and to break them down into alternative interpretable components. There's lots of lots of stuff. Well, these are like kind of like asset prices, and that's true. But the representations, and I'm going to produce representations that, at least to me, add some clarity to that as kind of a warm up to where I want to go. So I'm going to try to make the starting point simple and straightforward in a dynamic context. So I'm going to have a value function. I'm going to impose a set of controls. These can be suboptimal or optimal. They do not have to be optimal. But the key thing is I want to characterize the explicit state variable interactions between these objects. So if I'm going to be doing marginal valuation of one particular endogenous state variable, what's the implications that it has with interactions with other states? That's going to be very important. I will be deducing an asset pricing like formula with marginal utility adjustments. But then I'm going to push it further. I want to construct altered probability measures that adjust for various forms of uncertainty. And then I also want to introduce, I'm going to start off in a kind of a Brownian motion setup, but I want to introduce big infrequent jumps and see how they affect things and how I can modify the set of tools in order to accommodate those as well. And then once I kind of produce these representations, it's going to give me additive decompositions of the contributions to these marginal values, and then we can kind of assess which are the big ones and which are the small ones. There's a close cousin to this, and that has to do with, it's the analysis of states and co-state systems are well known in kind of dynamic systems analysis, especially under optimality. And of course, partial derivatives are also connected to co-states, and so obviously this would have to be in a mathematical equivalence. I'm not going to just be solving co-state equations, but I'm going to give a different type of representation, which I find to be pedagogically revealing. So this is not to help me solve models. This is to help me interpret models and help me to frame empirical challenges. Okay. So these type of examples that have occurred in the literature. So I mentioned the social cost of carbon, social value of research and development. So the social cost of carbon, of course, since Nordhaus's original work, there's been a lot of effort on that, trying to both model and measure it. Nature-based capital or natural capital. Dasgupta has been pushing this for but in ways, but both the Nordhaus and Dasgupta approaches really don't confront the uncertainty challenges. And then people talk about social capital. These very different objects are economically appealing, but there's measurement challenges that go along with them. There's modeling challenges that go along with them, and that's what I want to be opening the door to. I want to be able to I want to confront broad-based uncertainties arriving from imperfect measurement and quantification. For instance, what I engage in and have many conversations with my geoscientific colleagues who are experts in potentially future technologies to address climate change, and they can make guesses about probabilities, but they can't give you really super precise assessments, say these about payoff prospects and the like. And they're very much open to the fact that there's this basic level uncertainties should be factored into the analyses. And I think this carries over to the other measurement side, which I have on this slide here. So I'm going to start off with a kind of a simple diffusion dynamics. Remember, what I've done here is I've taken any controls, actions, and imposed them and made a Markov. So I just embedded these in the specifications of mu and the specifications of sigma here. dW is a standard multivariate Brownian motion. Okay. And then I'm going to construct what I'm going to call stochastic impulse responses. This type of construction does show up in other contexts. It's going to be closely connected to impulse response analyses in macrodynamics. It's like nonlinearities are going to be important. It's also been used in actually related ways in kind of the literature on derivatives claims pricing doing sensitivity analyses. But I'm not going to build those connections here. So I'm going to construct what I call a stochastic impulse response. Okay, and it's going to be a vector state measure variable that's going to measure the impact of a marginal change in any one or some combination of the initial states. And this is going to be a key part of the type of representations that interest me. So I'm going to form this vector process lambda And lambda is going to tell me if I change one of the states, I'll be able to tell from if I change one of the states, what's this going to do to all the other states. So I can initialize this process in different ways. I can initialize it at kind of one of the state variables of interest. I can do the social cost of carbon. You actually want to look across the multiple state variables, but I get to play with this initialization, and by this initialization, I can then trace out different types of marginal valuations. Now, this object, I call stochastic because in contrast to the kind of linear macro theory, it's going to evolve stochastically. It has kind of a well-known type of representation. This is, if you kind of mechanically apply the chain rule, you would kind of get this answer, but there's more mathematical delicacies behind it. I'm not going to jump into those. But if I take the ith component of this lambda has the same dimension as our states. So lambda super I is the ith entry of that. And so if imagine I'm moving one state at day 0, this is going to trace through what's going on to state I at day t. It's going to evolve stochastically like this. I'm going to go through and have to differentiate the drift. I'm going to differentiate the sigma with respect to x. And so it's going to behave stochastically because it's going to feed back on the x's here and potentially the Brownian motion. Now, linear vector autoregression analysis, this stuff is often used in macroeconomics. Mu is linear in the state, so that's constant, and sigma is not sigma's constant, so that term drops out. And so this turns out to then be deterministic. But in a general setting, these objects are going to be stochastic. So I'm going to take these stochastic impulse responses are going to be central to what I'm going to be displaying here shortly. Okay, so I'm going to consider some value function, say some discounted objective. As I indicated, I'm going to impose the optimal controls, or I'm going to suboptimal controls, and characterize these as dependencies. And then I'm going to investigate how these various marginal values depend on these partial derivatives and these stochastic responses, and then get this asset pricing-like characterization of these marginal valuations. So in the case of climate change, these variables will include something like temperature change, capital stock of knowledge for discovering new technologies. So I'm going to not show you all the details to how to get this, but you get this representation that's not terribly surprising, although I haven't seen it literally in this form here, because usually, we're used to working with kind of co-state representations for these marginal valuations, and this is going to be a scalar equation here, but it's going to involve more state variables. It's going to involve both x and lambda, and so what's going to happen is the lambda 0 here is just going to pick out which of these partial derivatives I care about. It's going to be this discounted expected objective, and it's got these two pieces to it. There's these stochastic responses, and there's a vector of those, one for each state, and then that's going to just dot in with a marginal utility as a function of that state. And so this by itself is no surprise, but I find it quite interesting and an important starting point for us. And so this does look like an asset pricing formula. There's like marginal utilities here. There are these stochastic responses are kind of critical in defining the corresponding payoff counterparts. So payoff counterparts are this dot product here. And you can start decomposing these by the different states if you like, because of the way this is represented. So if I want to look at the marginal value of marginal valuation of state 1, that's going to depend on how that state 1 affects all the other states. There's dynamic interaction here, and this is going to trace through all those effects for us. So if we think state interaction is a big deal, it's going to show up directly in this formula. And it's going to have some nice additive decompositions, which I can put to work. Now, I can sketch out how the logic works, because as I say, I think the formula as this is pretty intuitive. If I took just a whole vector of co-state equations, that'd be a vector system, and I could solve that. This has to be mathematically equivalent to doing that. But I'm able to write down this so-called Feynman-Kac partial differential equation by using the composite, both lambda as well as x. Okay, and so by introducing this lambda, it allows me to reduce this back to a scalar equation, and one that has this interpretation. These stochastic responses are very easy, have potentially measurement counterparts to them. So at the end of the day, I can get this single Feynman-Kak equation instead of the full vector system as would happen in co-state analysis. And then often co-state analysis was, you start imposing things like envelope conditions, which I'm specifically not doing here because it's going to enhance interpretation if I don't actually. So this is different than co-states, but it has to be mathematically equivalent to it. Okay, so here's the formula. I just wrote it again. And look at this flow term here. There's a partial derivative with respect of x dotted in with lambda. That has a contribution for each different state. So now I can figure out, okay, I have an additive decomposition state by state. And so state interactions now, how important they are, and showing in impacting the marginal valuation, the initial marginal valuation of any state are reflected completely in terms of these type of cross terms. So these are like, these social contributions to counterparts like dividends here, discounted, expected discounted, and then that's going to contribute to the initial marginal valuation. So this additive decomposition is nice, and these and at the heart of this are these kind of stochastic impulse responses. Now, let me just take a digression here. There's this National Academy's report. This shows up in 2017. It's a panel of experts. I know some of the experts. They're smart people. But they have this recommendation that I find really quite interesting. They want to take the social cost of carbon and they want to modularize it. And they want to break it down into 4 modules. There's going to be the social economic. That's going to be the starting point. Those are inputs. You feed those into a climate model, figure out what the temperature parts are, turn it over to environmental economists to figure out what the damages are, and then turn it over to the finance person to figure out how the discounting works. And this is their notion of integrated. I mean, this is literally what they're literally advocating, this 4-step procedure. Of course, if there's state interactions here, and if you start thinking about uncertainty at the same time, this stuff just kind of at least makes my head spin, because suppose in the future we start figuring out more stuff about damages than we know now, and that's going to have some policy impact. That policy impact is going to go ahead and then affect the social economic input into things, and there's going to be a feedback there. Of course, from asset pricing, it's not straight discounting you care about. It's you have to make uncertainty adjustments, so it's stochastic discounting that matters, and that's in turn going to interact with the social economic variable. So this prescription, I think, was way too limited. And if you read the paper, the report carefully, there are words of caution about it, and like this. But there are measurement papers, and a fair number of them, that really embrace this kind of modular system. And I wish things were not that simple. I just don't think they are. Okay. So suppose I just consider a state-dependent policy, then how does that interact with this stuff? So. Now, mu depends on some mu hat, and that's gamma of x. I think of gamma x as the policy rule. Think about a perturbation of that policy rule. Take gamma and perturb it by gamma bar. Then the marginal value of interest is just given by this partial derivative. And then you can use this to construct your initialization for lambda naught. In order to get this now, use this decomposition to figure out what's going to show up in the relevant marginal valuation that allows you to evaluate, that assesses policy. Okay, so far I've not really said anything about uncertainty. I've just got these kind of random shocks going on, these random Brownian motions going on, and that's it. So now I want to do is I want to add jumps, but I want to do it in a way that's not always applicable, but a way that's appealing for some examples that interest me. I'm going to think of these as very infrequent things. Okay, so this jump doesn't occur very, very, very often, and I'm going to analyze the problem from a perspective of what happened, how does the valuation work until the jump happens, and then how does the continuation values from the jump forward then contribute to the valuation. So these jumps are like, when I look at life cycle problems with terminal bequest motives and like that, it's in random life, it's going to behave somewhat similar to these type of structures. So I'm going to imagine there's a finite number of these different jumps. I could do the continuum case, but it's going to be a finite number of these. That I'm going to give them they're each going to be. The key thing here is these intensities are state dependent. Okay, so these jumps are going to depend on endogenous state variables, and so they're going to show up in valuation. And I'm going to give you some examples in which this is really central to the analysis. Think about making investments in research and development, and then down the road you make this really big discovery. Okay, so that's why it's a case in which your investments today are going to affect this intensity, and the more you invest in today, the more likely you make the discovery take place. Okay. Then we have a B super L. I have to tell you what's going to happen when the discovery takes place. There's a continuation value. That's what B super L is. Okay. So I'm now going to have these kind of these big L different type of terminal states that occur randomly, and then I'm going to take that into account in the valuation, and that's going to allow me to analyze these jumps. So if you work this through, then it's going to make what's going to happen is the following. It's going to have 3 different changes in kind of what I just showed you. The one, I start off with this constant discount rates. Okay, but now I've got this possibility of some type of event that's going to occur in the future. Okay, so I'm going to condition on that not happening, and in order to do the valuation, and then I'll take into account the jump prospects subsequently here. So I'm going to think of this as just like taking that state, that discount rate, and making it now state dependent, because it's going to depend on these jump intensities. So that's one adjustment. The other ones are adjustments. So this is adjustment to the discount rate. The other ones are adjustment to this utility, to these partial utility flows, the marginal utility flows. Okay, there's this. We've got the stochastic response here. Now, one contribution is the state variables, the endogenous state variables affect the jumps. So that's going to show up here, and that's going to then multiply what the difference is between jump continuation value, that's VL, minus don't jump. Okay. So this term just is added, and just like an additional contribution to the flow term into those being in the discount, in the expected discounted formula which I had previously. So this is one. It's the marginal impact of a jump. Okay, so if these intensities depend on endogenous stuff, then these terms show up. And in the examples I'm going to show you, that's going to be the case. Like as in this technology example, for instance, you discover the technology that's going to affect the continuation value, and the technology technology discovery, of course, will depend on certain investment choices. The other one is what happens to the marginal valuation should the jump take place, and that's this, and so that's the marginal impact of when you jump. So what I do is I take that previous formula now, and I just change the discount rate, and then I add in these 2 different marginal impacts to that marginal utility term which I had before. Okay? So these jumps can be tipping points, they can be big technology discoveries, or the like. Okay? So now I can, this gives me an extension of that formula, which I had now, which allows me to address some of these big events and their consequences on valuation. So now let me take a short break here and quote Hayek. That this is something that can haunt me at nighttime, I guess. Hayek wrote this essay. When you win a Nobel Prize, you have to write this essay, and you're supposed to explain why you won the Nobel Prize, which people get bored with quickly, and they write and they write other stuff. So Hayek writes this Nobel address, and he basically says econometrics is a bunch of BS. It just delivered nothing. Quantitative economics is a waste of time. It just is a language of mathematics should just be a language of clarity. So there's lots of this stuff which I think is interesting to read, but I don't fully agree with. But this particular quote, I think, has some salience, that even if true scientists should recognize the limits of studying human behavior, as long as the public has expectations, there will be people who pretend or believe they can do more to meet the popular demand than what is really in their power. And I think there is this kind of bias among economic advisors often to project themselves with excessive confidence, because that's the only way they can influence policy. And it'd be nice to work against that to some extent, because it's not necessarily true to the basic scientific knowledge base which we have. So that's anyway. So I want to try to incorporate. I'm going to incorporate some of advances in decision theory under uncertainty, and I'm going to first kind of use some stuff which has axiomatic representations, and then I'm going to also suggest it can be used in a somewhat different way than that literature intended. So decision theory aims to justify approaches that are called rational, but there's a whole bunch of different axiomatic systems that give rise to different representations. So maybe it doesn't reach a unique conclusion there. So maybe the term prudent is perhaps a better label for it. There's lots of discussion in public policy, including climate change, but a bunch of other public policy about so-called deep uncertainties. And it's the name is dropped all the time, but it's very seldom operationalized, and we're gonna make a stab at trying to operationalize it in some ways. So I want to kind of break uncertainty down into three components. Okay, one is you don't know outcomes, but you know probabilities, risk aversion, risk premia, and the like. When you do rational expectations models, we endow people with full commitment and probabilities. When we do subjective belief models, and it's like asset pricing and macroeconomics, we endow people with firm commitments to these alternative probabilities. So that's really risk. Okay. The next one is what happens if there's multiple models on the table. So there might be ambiguity across models, so there might be some form of prior uncertainty. Of course, we can go back to Savage, and Savage has this beautifully elegant axiomatic system, which I guess also related to work by Di Finetti, that says, well, subjective probability theory, that this is a way to justify it. But if you really look at Savage carefully and look at a bunch of his writings, I've been pushed on some of this stuff by Larry Samuelson and by Stephen Stigler, kind of trying to educate me more. And Savage himself has some skepticism about how far you can push his axiomatic representation. These subjective probabilities can only be known in great confidence in very simple setups, environments and the like. And so I'm going to kind of back off full commitment to probabilities here and suppose that there's some uncertainty about the probabilities. So there may be multiple models. I may have some type of subjective uncertainty about how to assign priors to them. This is, robust Bayesian methods have been exploring this topic for a long time. And so I'm going to be entertaining that as a form of ambiguity aversion, uncertainty about priors. The other one is probably the hardest one to wrestle with. It might be the most important one. This is true in microeconomics, but it's very much true in macroeconomics. We write down the models that are blatantly wrong, but we think they're interesting. And models kind of by their very nature are wrong. They're fundamentally misspecified. We go in econometrics classes, myself included, and teach people how to test for specification. But if you find a model's misspecified, that alone is not a terribly deep insight. What you care about is whether it's misspecified in a way that really matters, or if the misspecification is inconsequential. When we build models theoretically and conceptually, we abstract from certain things because we think they might not be important. So how do we treat models as approximations? How do we treat models that and acknowledge the fact that they're flawed? And so this is kind of this is kind of the third form of uncertainty. And I can produce various axiomatic treatments of these things. I'm not going to go into those today, but I'm going to use some of the representations. So we're going to endow our policymaker with preferences that encode these aversions. Okay? And as researchers, it's not my job to tell society how averse they should be. So I can't really. So I'm not going to tell you what that number should be. But what I can do is go through and look at the sensitivity to changing the aversions, and that's basically that's basically what we do. Okay, and so I think of these second and third components as capturing two forms of this so-called deep uncertainty. The ambiguity aversion is connected to robust Bayesian methods, and that's robust. Then the model misspecification aversion. There's aspects of this that have been wrestled with in the control theory literature for many decades now, and we'll kind of try to lever insights from both those sources. If you like axiomatic papers, I have mixed feelings about them, but here's a couple I like, I guess, because my name's on them. But anyway, I don't think they settled the issue. But I think they're interesting, of course. Now, all this is fine, but how does that connect to this valuation, which I want to do? So I'm going to adjust the valuation for model ambiguity or misspecification. I'm going to think about these as I don't I don't have full confidence in some baseline set of probability specifications. I might have a baseline prior, but I'm not fully confident in it. I've got some model, some baseline model, but I'm not fully confident in it. I'm going to be using that perspective. And so then to get an uncertainty adjustment, these are theories of aversion, just like a risk is a theory of risk aversion is aversion, is a theory of caution. I'm going to be looking over minimizations over probabilities, but then I'm going to have to impose some type of penalization over that. And these penalizations have to do with how averse you are to these uncertainties. And that's the nature of this kind of axiomatic representation theory, is kind of that mapping. And so literally in a decision problem, you're going to take a max problem and replace it by a max min game. But for every hypothetical choice of action, you're going to be looking over the different ways the model could be misspecified, priors or model misspecification, and figure out where's it most consequential. Where could that misspecification really cause issues for me? And then I'm going to try to isolate that aspect of it out. Now, even if this is going to turn out to be useful, even if I want to pose this as a problem of uncertainty quantification, which I'm going to come back to in just a minute. So formally, I'm going to use something called variational preferences. It's just a flexible way to represent a set of preferences. The structure, I'm going to have a kind of this ambiguity I'm going to think of as a form of structured uncertainty. I'm going to look at prior or posterior misspecification. In dynamic environments, I never know the difference between a prior and a posterior, because today's posterior is tomorrow's prior. But anyway, so we're going to look at robustness along those lines. And then I want to also look at more primitive probability misspecifications. I think about that as kind of more unstructured approaches to uncertainty. Now, if I do that minimization step, okay, that's going to produce an alternative probability measure. And it's a so-called worst case, but it's a constrained worst case. And it's one that looks at the decision problem and says, what aspects of this uncertainty really should matter to me? Okay? And it's going to isolate what that is. Okay? That's going to produce this so-called uncertainty, I'm going to call it uncertainty adjusted probability. And you can show in those marked evaluations that the object you want to use for the expectations are these uncertainty adjusted probabilities. This is a trick like people use in asset pricing when they do risk neutral probability evaluations. Well, I'm doing a different change of probability measure here. And this is going to adjust for these types of these uncertainty aversions. Okay, and we can formally justify that as the right thing to do here. And so this gives me a way to extend these marginal valuations and these decompositions in environments that have these different forms of uncertainty. Okay. Let me just say one thing here. Sorry, I'm going the wrong way here. I want to add one more thing. I mentioned literature on uncertainty quantification. There's huge work across many scientific disciplines on how to do uncertainty quantification. So we're looking at, suppose you take situations like, some of these measurement problems, nature-based capital, climate change and the like. There's a lot of different dimensions to the uncertainty. So you're thinking, you're facing all these different dimensions, and the uncertainty is potentially is very high dimensional. I can go through and I can quantify along each of these dimensions where the uncertainty is. But you want to take it one step further. You want to figure out along those big dimensions, how can I reduce that problem? And by solving this minimization problem, subject to these penalizations give me a way to parameterize that in that big dimensional uncertainty quantification into a much more narrowly defined sensitivity analysis, because now I just move these penalization parameters, and I find it to be a very useful way to proceed as well. So it gives me this way to refine uncertainty quantification by posing what the really policy problem is, and then having this minimization help me figure out where which parts of the uncertainty matter and which don't. So I'm going to sketch out in a very quick manner. I don't have time to really build the full model. It's just an example economy because I want to get to what I think is an interesting insight that uses these type of tools. I'm going to build an economy. It's going to be a very simple economy that allows me to address issues related to climate change. Now, a lot of the work on climate change treats technological progress as either exogenous or not present. Not all of it does. There is some work that has endogenous technological change in it. We're going to have. I'm going to make things really simple. I'm going to imagine that there's this Poisson component, and it's going to trigger a big technological breakdown. But breakdown. That's a slip. Breakthrough, advance. But maybe decades down the road. It might be like nuclear fusion, and maybe 3 decades provides us a much cleaner source of energy. But prospects are very, very highly uncertain. There's big debates. I've talked to geoscientists at MIT and Princeton that tell me that this is a very promising technology. I talk to my colleagues at University of Chicago and tell me that there's no way. I mean, there's a lot of heterogeneity about its prospects. If you think about some of the carbon capture technology that people are exploring, it's also a case there's a lot of uncertainty about when that stuff is really going to be actually viable and the like. So I'm thinking about those type of technological advances. Okay. And I actually think, there's lots of political problems during coordination of social costs of carbon and emissions policies and the like. I actually think technological breakthroughs may be our best, most promising way to address climate change, but that's just a personal opinion. But anyway, we want to include this into our analysis, and it's going to play a central role. So there's going to be 2 types of tipping points. One are these technological breakthroughs. These big events. One are technological breakthroughs. The other is I'm going to put on the table to get this trade-off between, do I want to act now or do I want to wait? So one of the arguments you hear in these uncertainty environments is, well, since we don't know now, let's just wait until we figure everything out. So I want to introduce that aspect of the problem. So there's lots of debates about damage functions. People in environmental economics use damage functions as simplifications about how they behave in the tail for more extreme changes in say, temperature. For instance, if you go back several years ago and compare the Nordhaus damage functions to the Weitzman ones, there are huge differences there. Okay, so I'm going to put uncertainty about that, about the tails of these damage functions. But down the road, as I warm, sooner or later, I'm going to get a lot more information about it. But there'll be damages which I incur along the way. So there's going to be a trade-off here between acting now versus waiting and learning stuff. And so I'm going to have this tipping point that's this information revelation that kind of once things warm enough, once the temperature goes up to a high enough point, it's going to trigger this informational event that tells you what the damage function is in the tail. And that gives me this way to just think about this trade-off between moving now versus moving later. I'm going to be the rest of today's doc, I'll be talking more about the second than the first. So our initial research kind of really pointed this, the way we set it up, is the unknown timing of the R&D investment was a really big contributor to the uncertainty part of it. The damage piece was there and non-trivial, but not nearly as potent. And then the uncertainty about the climate system was also there, but more marginal. But the other thing we stumbled on and want to explain is this source of uncertainty. If I crank up the aversion, if I remove my confidence in the probabilities of this R&D success, I'm going to end up doing more green R&D investment, not less. So this seems counterintuitive. I just made myself more uncertainty averse, and all of a sudden I want to do more. So what's going on there? Now, we do show that you kind of reduce emissions in the short run. We characterize this trade-off between acting now versus waiting. You do want to do some action now, and then you have more sharply responses when you figure out the damage function. But that's there. But I'm not going to be talking about that part so much here. So the model, it's going to be a simple AK technology, adjustment cost, dirty energy input. Output's going to be split between investment and standard investments. I want to have multiple investments on the table. And I think about a fictitious planner here. So it's going to be like optimal policy design. Output will split between investment in productive capital, investment in R&D knowledge capital, and consumption. There's going to be a climate externality. It's going to be a proportional reduction in consumption, and the damages are then linked to how much warming we do. So why would you want to do more proactive R&D here? So there's two forces here. One is that you adopt a more cautious view of the technology success. Okay? So that, if you think about an investment problem, and all of a sudden they say, well, I could invest in capital, or I can invest in R&D. And I trade off that investment. That alone, this effect alone is going to want to make you do less, because all of a sudden you're just less confident in the technological success. So that's going to be there. There's going to be a second force that can counterbalance it. And that has to do the following. And I'm going to show you formulas that get to this. Imagine you have a successful discovery. If you have a successful discovery, you just resolved a big chunk of uncertainty going forward. And so if you're uncertainty averse, that success is all the more is an even bigger deal. So the payoff to it, the endogenously determined payoff, is continuation values, gets bigger as you make the decision maker more averse because of the nature of the payoff. So there's a trade-off here. We ended up finding this. In our initial calculations, it was the second force which was dominating over a range of these uncertainty aversions. So this is not something, there's not some theorem here I can prove because these two forces working against each other. So here's the first one, okay? I'm going to strip it down to just abstract from the moment from the jumps in the realization of the damage function. Focus only on the jumps in the technology. Okay? Now I'm going to go across three different specifications of this aversion. Neutrality means that I just don't have this extra uncertainty aversion. I treat it as pure risk. I have full confidence in probabilities. And then I give you the kind of baseline payoff of this investment. And that's given by this blue histogram. I'm going to tell you the timing. So, the mode here is around 30 years. There's the median's a little bit higher than that. And so the blue line captures that. As I make these uncertainty adjustments, as I remove the caution, I'm solving that minimization problem. Especially the minimization problem is not your beliefs, but it's a way that you implement robustness. If I go part of the way, I get the green one, and that's like pushing this density after the right. If I go more aversive, push it all the more to the right. So this is the force that leads to doing less R&D. Because you just lose confidence in your ability to assign probabilities, and you treat that with caution. Okay, now there's the second force. Now remember these marginal terms I talked about that enter into the valuation coming from jumps. Think about the technology jump. Okay, if I make this investment in R&D, that's going to affect this endogenous state variables here, and then here's the payoff to having that R&D success. This V super L versus V. That gap gets bigger when this decision maker is uncertainty averse. Because under the uncertainty aversion, there's you just resolve a big chunk of that uncertainty, and so this payoff becomes bigger. There's a bigger payoff to doing the investment. So this is the force that leads to doing greater R&D. So there's just two things going on, and so it's critical here that we're computing these continuation values endogenously and the like, but those calculations are critical to this input. And so this is what pushes you in the other way: the success, the technology success, that payoff. Right? And so it's not monotone. Here's a table of which I can show you. I'm kind of showing the knowledge stock valuation. That's one of the, applying those marginal valuation formulas subject to these aversions. The C here is, as C gets smaller and smaller, you become more and more averse. These are like penalizations. The more you penalize, the more averse you are. And you can see what happens is the valuation starts increasing on you in ways, and then eventually it starts decaying. And then the associated R&D investment relative to output is just tracking that. It starts going up initially, substantially, like it's between infinity and 0.10, it's like we're like doubling it, and then basically doubling it again. So these are big impacts this is having, cranking up the uncertainty aversion. And it's all coming to that marginal payoff strategy, coming to a success. So it's just kind of verifies as non-monotone, but arguably in an interesting range we're getting these increases, which is so this is a case where you remove confidence, you actually want to do more of this investment, not less, because of the payoff. Currently, we're working, of course, the model I just described is way too simple. There's no heterogeneity and exposure to climate change. I put homogeneity in a bunch of places just to make the calculations really simple and transparent. We're now working, and this requires more extensive numerical calculations as well. In there being states, which we're working on distributions over kind of potentially continuous states. There's going to be an infinite dimensional state variable that has to do with this distribution. For policymakers, the allocations have to do with actions as functions of the individual and aggregate states. So the aggregate states is distribution, and the individuals will face their own individual state variables. So the counterpart, for the planner is this aggregate state variable, which is this distribution which is evolving stochastically over time. Because we have aggregate shocks, and that's going to induce the stochastic evolution. We incorporate robustness adjustments from both individual and area dynamics, and then we have to solve this using global solution methods. We're basically, there's literature on mean field games there's been a lot of work on recently. This is kind of the mean field control counterpart to it. And then for us to do it, it's also some important numerical challenges as well. But this allows us to have heterogeneous exposures to the climate change and heterogeneous damages too, which are kind of known to be quite important. As I look across different regions of the world, there's obvious heterogeneities there, and so it's the plan is then to think about how to extend this marginal valuation toolkit in order to analyze these problems as well. So we're making progress on the solutions part of this stuff, and we're working hard to try to make this a tractable approach and tractable extension. So let me just conclude. Sometimes the best response to uncertainty is to be more proactive. This uncertainty aversion. I think more transparency in scientific communication can lead to better policy. I think this idea of like pretending you know more than you do can be dangerous. I think these characterizations of the marginal valuations and those associated decompositions, including that the state dependencies, can be very important. Those modular approaches abstract from those state dependencies, but they're also, once you start putting uncertainties, uncertainties interact across these different pieces. So I think these formulas help to reveal that state interaction in kind of nice ways. And so I think of this research as supporting explorations in uncertainty in both private and public sector decision making, and the deconstruction of implications and the measurement input, I think, can be useful as well. And these deconstruction tools, I didn't have time to elaborate here, but you can take a model with a whole bunch of different pieces, figure out which part really matters, and then you can give stripped down versions to illustrate the basic mechanism without having the full complexity. So there's a deconstruction step of models here, which I think can also be valuable. I think it can support measurement, but it can also support taking seemingly complex models and kind of figure out what really drives them. Anyway, thanks for listening, and that's what I have to say.
Thank you, Lars, for staying strictly on the time. And I think we have time for a couple of questions. Let me start taking advantage that I'm here. Listen to you, it seems to me that COVID is a kind of interesting example for that, in which you have the virus and the socioeconomic and the social distance. And at the same time, you have the technology in which, when you push a lot of money to it, it got the breakthrough, right? So, yeah. I mean, to what extent, you can have somehow some way of quantifying what is the impact of ignoring those state dependency in real problems, and I think it would be interesting.
So I think pandemics are a very interesting question. But if you look at the models coming out of COVID, sometimes they were used to produce best guesses, and sometimes they were used to provide warnings of what bad things could happen. And the uses of them were not always made clear when results were announced. Both uses are, of course, interesting, the challenge us for there is we do start with baseline probabilities. So we do have to have some type of baseline guesses. And so you would have to start from somewhere with the pandemics. And if you kind of say you don't know anything, then this stuff can become much less valuable. So there has to be at least partial knowledge, or we can't really get off the ground very far. But I do think stuff like, pandemics are potentially something that we're thinking about.
Questions? Is there another mic? I can speak up. You can speak up. Okay, fine.
I'm curious in your model. We talked about two channels of uncertainty through which R&D investment and opposing forces. But what about another channel in which you invest a lot in R&D? Say you discover new therapy, and you never get a chance to actually learn about the magnitude of damage, right? So you eliminate the problem, but maybe it turns out the damages of climate change isn't so bad. Is that a third channel that works in your model that actually kind of works in the forces here?
So we have that channel partially, not in the results I showed you. So when there's this damage event happens, the damage realization can be good news. It can be damages are going to be very, 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 very modest. And in those sorts of circumstances, you start reducing substantially how much you're investing in this R&D because because climate change isn't nearly as big a problem as you thought it was. So that force is there. It's not illustrated here, but there is that force in our basic model, in our bigger model. Yes.
Anyone else? Oh, Jose.
Have you ever tried to get some estimates of the rate of return you're going to get for marginal valuation?
Yeah.
Give you something like a rate of return for your next dollar.
Yeah.
And that gives you some idea.
I mean, presumably one could translate that into what we're doing to that. I mean, I haven't really kind of written in those terms, but in principle, that should be doable. I should add, there's two type of extensions. One we've done stuff on, and the other one I'm engaged with some geoscience colleagues to explore as well. The first is, people bug us about this. Oh, there's just this one jump here. What happens if you have multiple jumps? And we've explored that. Of course, it's going to have quantitative impacts. This thing's not going to. This doesn't disappear, but we do have multiple stages. We just want to illustrate it in a simple possible way. The other one, though, I think is much more important, and that is that there's multiple different. Society's going to face which of these uncertainty technologies to address climate change should I be investing in? How much should I put in investing in the future of carbon capture, nuclear fusion, and various different technologies. I've got a colleague at Chicago, David Keith, who's going to shoot aerosols way up in the atmosphere and then delay the climate change problem that way. And there's still some research that needs to be done but before that's fully viable too. So, but I think this trade-off between policies, but between investment policies can be very important here, and that's something which I'm keenly interested in, and that's abstracted from in this example. Yeah.
One important policy question right now. It's very expensive to use CO2 emissions in certain situations. Right?
Yeah.
So the question that you pay that money because given the magnitude of CO2 emissions that very bad, or you prefer to direct that money towards R&D. That's something you have there.
Yeah. No. We may not have kind of calibrated in quite the most interesting way there, but absolutely. I mean, that trade-off is in here. Yeah, absolutely. I agree with that. Yeah. I mean, I want to be clear. There is a variety of other work that's been done with the R&D, endogenous R&D for climate change, like but most of that work abstracts from the uncertainty part of it. And so what we're adding is we're not introducing R&D and climate problems. Although it's remarkable how many of these social cost of carbon measurements leave it out, but but that's been addressed. I think what we're trying to do is put the uncertainty concerns, and that's what's I think somewhat novel here. And then this trade-off between these two forces that work in opposite directions.
Okay, thank you so much for staying with us until now. Let's thank Lars once again. Thank you, Lars.